So after talking about tendons and ligaments, I think it's time now to talk about muscles. So now muscles are responsible for applying force to create movements. And those can also be used to stabilize joints. So they also play a role in stabilization. To begin with, muscles are the largest tissue mass in the body. And if you know anything about muscles, they have so much protein in them. Vary in size, shape, and ability. There are muscles of the eyes, and there are muscles of the biceps. Different strength, different size, and different abilities. Muscles contain many parallel cells. Many parallel cells, known as sacraloma, and these cells are filled with fibers, myosin fibers, that can convert chemical energy into mechanical energy. And I didn't draw the diagram over here, but if you see a diagram of muscle cells, how it works is neurons from the spine will go to the muscle cell, sometimes 1, sometimes 50, sometimes 100, and they send a signal to the muscle cell to contract. So now, what are the responses of the muscle now? There's a twitch response, this initial response. You apply a signal, and then the muscle is going to respond, produce some contracting force, and then another signal happens, it's going to contract again. Now, when a repeated stimulus occurs, what's known as incomplete tetanus forms. The stimulus is gonna come, it's gonna contract, and then before it can relax, another stimulus is gonna come, so it's gonna contract again, and then another stimulus is gonna come, so it's gonna contract again, and it can only do that up to a maximum point where it cannot contract any farther than that. So like an adding effect. While it's contracting, another contraction happens, and so it will contract even more. And so the force can be increased. And then eventually you can have a complete tetanus. Once the muscle gets used to it, you keep on firing it at very high speed, the muscle is just going to almost exponentially here. You can see it's just going to rise up and then smoothly just start to contract. And this you can see in many cases, like if you move your arm and the likes of it, very fast contraction, that when you add them up, really, it doesn't look like at all being individual signals coming in. It will look as if it's just a continuous signal. This is known as complete tetanus. So quickly, relationship. The relationship of the force of the muscle to its length. So now we're looking at the length of the muscle. As the distance increases, as the muscle gets stretched. So let's say stretched. This muscle is going to try to resist the stretching. So if you're trying to hold a weight, and the weight's trying to, through the moment produced, trying to pull your arms down, the muscle is going to try to resist that. So if you have an arm over here and there's a weight trying to pull it down, this arm wants to go down, the muscle is going to resist that, produce a force this way. But it's going to, nonetheless, let's say if that's not happening, it's nonetheless going to be stretched. Let's say the force is not enough. So what's going to happen? Eventually, once it increases a little bit, the force is going to rise up, and then when it starts to increase even more, when this length starts to increase even more, the force is going to try to increase, up to the point when you're down here, and I don't know if it's focused. Let me try to focus it again. Sorry about that. Up until when you're down here, then the active portion, the muscle cannot produce enough force, and that's, if you look at the anatomy level, muscles basically are myosin heads with the filaments. So really, once you stretch these up to a certain point, once they're stretched up to a certain point, they don't have that much grip to be able to produce a contracting force. So eventually, the farther they are, the less of these myosin heads can actually produce a contracting force. And so once you stretch it, the active force of the muscle won't be able to withhold this weight anymore. But because the muscle is viscoelastic in itself, is instead of producing chemical energy to produce the counteractive force, is going to rely on the muscle itself being viscoelastic to absorb the energy like a rubber band, like to force it, like a tight rubbery string, just to force it back. And so after a certain point, once the active part dies out, you'll notice the passive part, that elastic part, is going to be kicking in, and eventually it's going to start to resist the force, and then it will increase exponentially until eventually you can't apply any more force, it's just going to fracture. So the total force follows this trend. It increases and then drops a little bit and then will continue to increase. This region you really wouldn't want it because that's actual material stress on the muscle cells. So if we look over here, this related more to the other part. I don't know why I went to this part, but okay, let me just explain this. Distance versus time. If a stimulus comes in and there's a light force, so you're holding a really empty water bottle, and the stimulus comes in, you'll notice that you can react so much more quickly. You can begin to move that water bottle so much more quickly, and with that single stimuli, you can move the water bottle much more farther. And the reason you can move much more farther is because the muscle can contract much more farther. So if I draw like a muscle over here, a bone over here, and I have a cup, let's say over here, and I apply a muscle, if I contract the muscle from here to this point, my new position will be over here. So if I can move the cup much more farther, it means I contracted the muscle much more farther. And that's because it's a light stimulus. So it's a light object. If it's a light object, which means I'm applying a light force, number one, I respond quicker, and number two, I can move more distance. If it's medium, it's going to follow the same trend. And when it's heavy, it takes a lot longer for the stimulus to begin the motion. So if this is, let's say, a weight now, if you're carrying a weight with a heavy force down, what's going to happen is that initially when it comes in, it's going to have to take a time before it can slowly start kicking in. And when it moves, it's only going to move a little bit, only a little bit. So your new position will be something like this. And you notice it's also going to die off quicker. And it's going to take more time for it to relax. And this can be explained nicely with the force-velocity relationship. So we have a force, and we have velocity of the muscle. Velocity of the muscle, that's the key. This is the velocity of the muscle fibers. Which, if you're comparing it to weight, it can mean the weight. So let's say you're lying down and holding a weight up. So let's say you're a person over here. I'm going to draw a rough sketch. And you're holding a weight up. Let's assume you cannot lift the weight any higher than you are. Let's assume this position is the highest you can ever lift it. That means you're isometric. The velocity is zero. Your muscles are not moving, and that's why they can hold it. So the force they can apply this is the maximum force they can hold a stationary object. What if the velocity was positive? In other words, it was actually contracting. So if I would contract the muscle, it means I'm applying force, which means I'm lifting this up. Contracting the right muscle would lift this thing up. If I were to contract it, then you can see that the faster I want to move it, the less force I can actually apply. The faster I want to move this object, the less force I can apply. So if this object was, let's say, at a force of this much, I could not move it any faster than, let's say this is 2 centimeters a second. Let's say this is 2 centimeters a second. I could not move this object any faster than 2 centimeters